from Vibhutesh sir, HOD
This call is
ENTC.
now being recorded.
So in this mail, it is given that this mail is from Coursera. So this is the statistics of all the courses. So for Coursera, total enrollments are 1,480, 14,480. So all this information is there in the tabular form, and still uh, total course completions are 4,520, and the courses which are just enrolled, but have not enrolled 55, who have enrolled in the course but have not completed any course, those are 506. Learners who have enrolled in one courses are like this, 178. And learners who have completed more than two courses are 619. Okay, these statistics came from Coursera itself to our college, and through Vibhute sir it is coming to us. So just one request to all of you that uh, we are having the free Coursera courses completion facility up to September end. Previously it was up to something 31st of July, but the date is extended up to uh, 30th of September. Okay, so try to take maximum benefit out of it. Not necessary means uh, verbal non-verbal type of courses are also there for your letter writing, making the presentation and all these things. So that also you can go through in this particular period. And definitely the courses which are technical that you are already going through, because I'm finding many of the certificates posted on LinkedIn as well as on Facebook, etc. So you are on a right track. But with this, you can go for some many more courses as well. Okay, so take serious note of it and complete as many courses as you can. Okay, so still some discussion is there in the chat that if your name is there in the Excel sheet, it is already there with you on group as well as on mail. So if your name is there in the list, no problem. If not, then fill the information immediately so that it will be available with our TPO department. So, two important things I have already shared with you regarding Coursera and regarding your enrollment for TPO data. Now we will go for our unit, unit second that we are going through. So we have gone through the introduction part of the chapter. Then we have seen the desirable features of good message passing, including the simplicity, uniform semantics, efficiency, reliability, correctness, flexibility, security, and portability. Then, with this, we have seen the issues in IPC message passing, in which we have started with the actual message format. So, you can get question of about 2 marks or 4 marks. So what is the format of your message? So that time you can explain this diagram and the issues, whatever the issues in IPC message passing. So you have to explain any four or many, any four or six out of these issues. Then we have started with synchronization yesterday. So in that we have seen the difference between the blocking type and unblocking type, sorry, non-blocking type. With this, we have seen the method of polling and interrupt. Then this diagram we have seen for the synchronization process, how the synchronization exactly happens. So from the sender side and receiver side, how the message is transferred and for what time or what period, how much period you are there in the blocked state and executing state, that all things will be explained by this diagram. Then we have started with buffering part. So in that we have seen four basic types of buffering. So in that for synchronous we are having null buffer or no buffering and buffer with unbounded capacity. And in case of asynchronous we are having single message and finite bound or multiple message type of buffers. So we have gone through each and every part of this buffering. So first is null buffer. So in this null buffer, we are not having any kind of um, facility of saving your messages anywhere. Your sending process directly interacting with the receiving process. So diagrammatic representation yesterday we have seen for this. So whenever you are explaining each and every part of this, you have to draw the diagram. Okay. I think in the last exam, that is November December 19, one question was there on this particular part. What is buffering and what are the different types of buffering? And it was for 6 marks. So what is buffering and its details were for 2 marks, and types description 4 marks. Something 6 marks question was there. So this first is null buffering or no buffering. Then single message buffer. So in this you are having facility to store one single message at a time. So it is also represented with diagram in this way. So here node boundary is there for sending process, to differentiate between sending process and receiving process, and your single message buffer will be there at the receiving side. So whenever sending message or sending process is sending the message, it will be stored in the buffer, and whenever receiver accepts that message, then and then only it will be given to the receiver, and that time your buffer becomes empty. Then unbounded capacity buffer. So here the name itself suggests that it is not having any capacity for the buffer. So whenever the messages are coming, you are just storing at some place and then giving it to the respective receiver. So it is not having any kind of boundary over here. But for actual implementation, it is difficult to implement by using our programming languages. So we are going for the fourth type, that is finite bound or multiple messages. So here this particular buffer you are mm, for this buffer you are giving some kind of capacity. So n number of messages will be stored over there, and on the first come first serve basis the messages will be transferred from sending process to the receiving process. So up to this part we have seen in our last lecture. And then the next part is multi-datagram messages. So it is just the theoretical part. It is not yet asked in the exam. So maybe the font is a bit smaller one. Whenever you will be getting this particular PPT with you, then you can go through the details of it. But I think it is somehow visible to you. So, so what is multi-datagram messages? That is, almost all the networks have an upper bound on the size of data that can be transmitted at a time. So this size is known as maximum transfer unit (MTU) of a network. So at a time, how many messages we can send? So that maximum transfer limit is set by your network, that is called as a MTU. A message whose size is greater than MTU has to be fragmented into multiples of the MTU, and then each fragment has to be sent separately. Okay, so each fragment is sent in a packet that has some control information in addition to the message data, and this each packet is known as a datagram. So whenever you are sending the message, if it is having size more than your set MTU, then it will be fragmented and then will be sent to the receiver. So in this, each and every packet is known as the datagram. So messages smaller than the MTU of the network can be sent in a single packet and are known as a single datagram messages. So delivery of one single message at a time, we are calling it as a single datagram messages, and vice versa. Or on the other hand, messages larger than the MTU of the network have to be fragmented and sent in multiple packets. Such messages are known as multi-datagram messages. So this kind of question can be asked for just MCQ type of question. Okay, so obviously different packets of a multi-datagram messages bear a sequential relationship to one another. Why sequential? So which particular packet is coming after the first one? Okay, so that particular sequence we have to maintain. Otherwise, we will be getting um, the data which is not can or cannot be understood by the receiver. So it should be sequential one. The disassembling of a multi-datagram messages into multiple packets on the sender side and the reassembling of the packets on the receiver side is usually the responsibility of message passing system. Okay, so just the single datagram messages and multi datagram messages, this concept is described in this particular bit. Okay, so how to fragment it and how to disassembling it and reassembling it, that is not the part. It is coming for just the theoretical part. Okay, so this is multi datagram messages. Then coming to the um, very important part of this topic, that is encoding and decoding of the messages. So in case of computer network, have you gone through encoding and decoding of the message data or any kind of data? Have you gone through this kind of programming before? Any kind of encoding and decoding of data, that kind of programming till now? Yes, very good example about sending the password and retrieving your data present in maybe banking website or your Gmail inbox or anywhere, any kind of information related to your password. Okay. Related to this, any kind of programming, not exactly related to password or the that kind of things, but you are sending some message to the receiver, but in the encrypted form, and then it is decrypted at the receiver side, and then he will be recognizing the data that is transferred from the sender. Anything related to public key, private key concept, ciphertext, might have studied in case of computer networks. No one else is responding. Okay. So encoding and decoding of message data. A message data should be meaningful to the receiving process. Just now I told that if at the sender side your message is encrypted, but if it is not properly decrypted at the receiver side and he is not able to recognize whatever the data that is sent by the sender, then it is of no use. Okay, so whatever the exact data that is being transferred from your sender, that exactly should be received to your receiver. So this implies that ideally the structure of a program object should be presented while they are being transmitted from the address space of the sending process to the address space of the receiving process. So this obviously is not possible in case of heterogeneous system in which the sending and receiving processes are on the computers of different architectures. In first chapter only we have seen the structure of heterogeneous system, that is each and every system is having its own architecture. Okay, it will be having different OSs, different everything different. Okay, not only OSs but all the softwares also. If one machine is on a Windows platform, another is on Linux platform or Unix platform. So here on Windows you are having Microsoft Office, on that machine you are having LibreOffice. Okay, so this is just the basic thing, but there are many programs which are um, absolutely different one. If you are setting your PowerPoint presentation in case of Windows platform with some काय म्हणायचं, layout, but it could be different on your Unix platform. Okay, so while sending your data from one machine to another, which are in heterogeneous system, it will be very difficult. However, even in homogeneous systems also, it is very difficult to achieve this goal, mainly because of two reasons. In case of homogeneous also, it is very difficult, and it is having two reasons. That first one is an absolute pointer value loses its meaning when transferred from one process address space to another. Therefore, such program objects that use absolute pointer values cannot be transferred in their original form, and some other form of representation must be used to transfer them. Okay, so here in this case, whatever data that you are sending, if the absolute pointer value, if it is losing its meaning, then it will be difficult to receive that particular message in the original form. This is the first reason. And second is, different program objects occupy varying amount of storage space. So to be meaningful, a message must normally contain several types of program objects such as long integer, short integers, variable length character strings, and so on. So in this case, to make the message meaningful to the receiver, there must be some way for the receiver to identify which program object is stored where in the message buffer and how much space each program object occupies. So your you will be storing all this information, maybe in the form of table. So which particular process, how much space, disk space it is allocating, and what are the different types of objects it is including. Okay, so maybe it is a long integer, short integer, variable length data. All this information will be stored in the form of a table, and that will be sent in this message passing. So due to the problems mentioned above in transferring the program objects in their original form, they are first converted to a stream form that is suitable for transmission and placed into a message buffer. This conversion process takes place on the sender side and is known as encoding of message data. Okay, so whatever the data stream that is there at the sender side, it will be converted in the form of stream, and then it will be sent to the receiver. So this conversion is nothing but the encoding of the message data. And then at the opposite side, the encoded message, when received by the receiver, must be converted back from the stream form to the original program objects before it can be used. The process of reconstruction of a program objects from message data on the receiver side is known as decoding of the data. Okay, so suppose for example, you want to um, um, send the family tree something. Okay, family tree to your friend, but it is in the uh, encoded form. Okay, so tree structure, what to convert it in the form of string or linear data, what you can use in case of tree. गेटिंग द क्वेश्चन. मला एखादा ट्री लाईक स्ट्रक्चर रिसिव्हरकडे पाठवायचं आहे, तर त्याची इमेज वगैरे मी नाही पाठवू शकणार. ठीक आहे, सपोज ABCDE असं काहीतरी आहे. ए हा तुमचा रूट नोड आहे, त्याचे चाइल्ड आहेत B आणि C, आणि पुन्हा खाली बी चे चाइल्ड आहेत डी आणि ई असं काहीतरी स्ट्रक्चर आहे आणि ते तुम्हाला सेंड करायचंय एका रिसिव्हरला. पण हा डेटा इतका इम्पॉर्टंट आहे की तो तुम्हाला एन्क्रिप्ट करायचा आहे. तर तुम्ही काय कराल? एन्क्रिप्ट इन द सेन्स आता या केसमध्ये तुम्हाला त्याचं स्ट्रीमिंग करायचं, स्ट्रीमिंग किंवा त्याला एका लिनियर फॉर्म मध्ये स्ट्रिंग फॉर्म मध्ये कन्वर्ट करायचंय. काय कराल तुम्ही? All right. So suppose for example, I'm sending this particular tree-like structure in the form of infix. Okay. But the receiver is getting the information that he will be receiving the uh, string in the form of prefix. Whether he will be getting the exact data what I have sent to him. No. Right. So the places of leaf nodes or the root node may be fixed, but other nodes may get changed in their places. Okay. So whatever the data that is been encoded and decoded from the sender and receiver side respectively, so how they are going to be encrypted or decrypted, that is known to both of the um, involved parties, right? So one of the following two representations may be used for the encoding and decoding of the message data, in which the first one is in tagged representation. So the first is tagged representation. The type of each program object. Am I audible clearly? Rohit? Okay. So first one is in case of tagged representation, the type of each program object along with its value is encoded in the message. In this method, it is simple matter for receiving the process to check the type of each program object in the message because of the self-describing nature of the coded data format. So this is the tagged representation in which you are giving the um, program object as well as its value. Okay. And with this information receiver may get the idea that how I'm going to um, decrypt the given data. And the second format is in case of untagged representation. So the message data only contains the program objects. No information is included in the message data to specify the type of each program object. So in this method, the receiving process must have a prior knowledge of how to decode the received data because the coded data format is not self-describing. So tagged मध्ये काय असणार आहे की कशा पद्धतीने you are going to decrypt that data. So its description will be there, but in case of untagged, it is not. So prior, this information should be there with your receiver. So suppose for example, I am writing the uh, data like ABC, okay, and I am sending it in the encrypted form like A, D, B, D, C. Okay. So after each and every bit, I have inserted one letter, that is D, D in between. Okay. So this kind of um, insertion of the insertion of the D or some such kind of letter is there. This information should be there with your receiver, so that whenever he is getting that encrypted format data, he should be able to decrypt it and get the meaning of the original data. Okay. So this prior information should be there with receiver. If not, so if this scenario is there, then it is called as a untagged data. And if both the information related to program object as well as the value in the encoded value encoded in the message, if it is there, then we can call it as a tagged representation. So in general, um, tagged representation is more expensive than untagged representation, both in terms of the quantity of the data transferred and processing time needed at each side to encode and decode the message data. So tagged representationच्या केसमध्ये why we can say that it is more expensive, आता इथे दिलेलंच आहे इन टर्म्स ऑफ क्वांटिटी ऑफ डेटा ट्रान्सफर. आता टॅग्ड रिप्रेझेंटेशन तुम्ही करत आहात, तर त्यामध्ये काय करायचंय तुम्हाला की अलॉंग विथ इट्स व्हॅल्यू इज एन्कोडेड इन द मेसेज डेटा. ओके. आणि प्रोग्राम ऑब्जेक्ट हे दोन्ही तुम्ही सेंड केलेले आहेत, त्यामुळे डेफिनेटली द लेंथ ऑफ quantity of data, that is the length of the data, will get increased. And again, there are chances of this data getting hacked, so kind of security also you have to provide with this particular data. Then no matter which representation is used, both the sender and the receiver must be fully aware of format of the data coded in the message. That is there, no doubt. दोन्ही साईडला दोन्ही पार्टीजना माहित असायला पाहिजे की डेटा कुठल्या फॉर्म मध्ये एनकोड होऊन येतो आहे. ओके. द सेंडर possesses the encoding routine for the coded data format and the receiver possesses the corresponding decoding routine. The encoding and decoding operations are perfectly symmetrical in the sense that decoding exactly reproduces the data that was encoded, allowing for differences in local representation. Local representation is what? How I'm going to represent that data with my team. So that is nothing but the local representation. But whatever the original data is there, that should be unique in both the cases, or for both the parties. Sometimes a receiver may receive a badly encoded data, such as encoded data that exceeds a maximum length argument. In such a situation, the receiver cannot successfully decode the received data and normally returns an error message to the sender indicating that the data is not intelligible. Intelligible means it is not properly recognizable. Okay. So this is the situation when the receiver is not getting what exactly the sender has sent. So at that time, the receiver may send the error message to the sender that he is not recognizing, or your data is not intelligible, cannot be easily recognizable. So this is encoding and decoding of message data. Might be based on this particular point. There is a one program in the list. I think it will be there. I have to check the practical list also. If it is there, some kind of with some minor encryption and decryption, we can perform that particular program if it is there. Okay. So this is nothing but the encoding and decoding of message data. So only the question what is encoding and what is decoding, that kind of question can be asked. So any doubt in this? ऑनलाईन फक्त एकटेच आहेत का काय? बाकीचे सगळे झोपले? At least 4-5 responses should be there in the chat window. मला काय झालंय? Okay, no problem. So the next bit is process addressing. So another important issue in message based communication is addressing or naming of the parties involved in the interaction. So that is, to whom does the sender wish to send its message, and conversely, from whom does the receiver wish to accept the message. Okay, so in your message passing, who are the different entities involved? The sender and receiver. So who is the sender, who is the receiver, that should be addressed properly. So for greater flexibility, a message passing system usually supports two types of process addressing, and that are, the first is explicit addressing. So here the process with which communication is desired is explicitly named as a parameter in the communication primitive used. So here in the diagram, primitive A and B are given, which are the examples of explicit process addressing. So in case of send, here the send primitive will be having the process ID and message. So it will send a message to the process identified by the process ID. And the next is receive primitive. It will also have the same arguments, that is process ID and your message. So it will receive a message from the process identified by the process ID. So in case of send, this process ID will be which particular process ID? Process ID of a sender or receiver? Yes. In the send primitive, send a message to the process identified by process ID. It is given. So this process ID will be the ID from sender or receiver. Yes, it is receiver. And in case of receive message, the process ID will be of the sender. Only 38 students are there in the chat or in this particular meeting. I'll comment on this after the lecture. And then this is explicit addressing, and second is implicit addressing. So in this, a process willing to communicate does not explicitly name a process for a communication. So here the primitives C and D of the figure supports the implicit process addressing. So here in case of the send message, it will be having send any, and the service ID will be there, and then your message. So what does it mean? Send a message to any process that provides the service of type service ID. Okay. So here we are not involving the processes, but we are involving the services over here. And next is receive any. So here also you are having process ID and the message. So receive a message from any process and return the process identifier, that is process ID of the process from which the message was received. So previous case एक्सप्लिसिट ॲड्रेसिंगच्या केसमध्ये काय करणार आहे आपण, सेंड आणि रिसीव्ह प्रिमिटिव्ह जे काही आहेत आपले, तर त्यामध्ये वी आर एक्सप्लिसिटली रायटिंग द identifier or address of the process to whom I am going to send the data, or the idea of that particular process from where I am getting that particular data. So maybe here your IP address or any location identifier, that from this location I am getting the data. This kind of details will be there in case of process ID. So whenever you are involved in one-to-one kind of message delivery, message transfer, at that time you will be having definite process IDs. But here in this case, implicit addressing, we are involving the servers in that. Okay. So for server, uh, for on which particular server, which particular data is present. Okay. Or if we are having 2 3 servers, so from which particular server you are getting your respective data. So suppose for example 5 servers are there, 1 2 3 4 5, and you have fetched one query and it is diverted to server number 3. So you will be getting the data from server number 3, but that is unaware to the um, receiver or the user. Okay. So here I will be sending the data with the service ID that I want this particular service like that. Then you will be receiving the data from that particular server itself, that this is your requested data, or this is your required data. Okay. So in this way implicit addressing will be working. So a simple method to identify a process is by a combination of machine ID and local ID, such as machine ID at the rate local ID. So या केसमध्ये if you are working in a particular network, then how each and every machine will be addressed. So the machine ID at local ID. In this way the nomenclature will be done. So the local ID part of this particular machine ID underscore local ID is a process identifier or a port identifier of the receiving process, or something else that can be used to uniquely identify a process on a machine. Okay. So this is your local ID part. And secondly, the machine ID part of the address is used by sending machine's kernel to send the message to the receiving process machine. And the local ID part of the address is then used by the kernel of the receiving process machine to forward the message to the process for which it is indented. So this is the difference between machine ID and the local ID. Local ID part will identify which particular port identifier you are using, and machine ID is related to the kernel. ओके, जसं की आता आपण सपोज लॅबच्या एक्झाम्पल मध्ये जर बघितलं, इफ आय एम हॅव्हिंग नंबर 15 machine in the database lab of the CSC department. So how I will be giving the address over here? मशीन नंबर सपोज CSC डिपार्टमेंट, CS वरून काहीतरी आपण नावं दिलेली आहेत. सो CS 15 DBL, that is database lab, CS and COE. ओके, म्हणजे COE कॉलेज मधल्या CS किंवा CSC डिपार्टमेंट मधल्या DBL डेटाबेस लॅब मधलं 15 नंबरचं मशीन. सो हे अशा पद्धतीने आपल्याला नॉमेनक्लेचर करावं लागणार आहे की जेणेकरून आय कॅन आयडेंटिफाय विच पर्टिक्युलर machine is involved in the process. Okay, so I shared one incidence with you in our first or second lecture about what our DNS server something like right. So after that incidence, our each and every machine has given unique name, so that whenever you are getting any kind of data, you can identify from which machine it is delivered. Okay, so for that process purpose you need proper kind of addressing. So for this, what are the different features, attractive feature of this kind of machine ID underscore local ID, this kind of addressing we have used. So it is having the attractive feature like no global coordination is needed to generate the system-wide unique process identifier, because local IDs need to be unique only for one machine and can be generated locally without consultation with other machines. So it will be unique for this case, limited part of the किंवा एका पर्टिक्युलर कॅम्पसच्या दृष्टीने वगैरे म्हणाले लिमिटेड नंबर ऑफ रिसोर्सेस असतील तर त्या केसमध्ये इट विल बी गुड वन. बट इट इज हॅव्हिंग द ड्रॉबॅक लाईक it does not allow a process to migrate from one machine to another if such a need arises. For instance, one or more processes of a heavily loaded machine may be migrated to a lightly loaded machine to balance the overall system load. So आता जसं एक्झाम्पल सांगितलं, in our DBL lab 15 number machine, if it is required in say for example ENTC department in their one of the labs, something project lab from ENTC department. Okay, so can I directly shift that machine to ENTC? No. So for this purpose I have to change the addressing for that machine and then have to shift. Okay, or suppose for example I want to share the load present on that machine. सर्व्हर आहे माझं, त्याच्यावरती खूप सारा लोड येते असं मला वाटलं, तर त्याचं शेअरिंग करत असताना हे जे काही ॲड्रेसिंग आहे ते प्रॉपरली मेंटेन तुमचं होणं गरजेचं आहे. then and then only it will be possible. So this is the drawback. So to overcome this, we are having the processes can be identified by the combination of following three fields, that is machine ID, local ID, and again the machine ID. So the first machine ID or the first field identifies the node on which the process is created. So this machine ID is related to that machine only. जे मशीनचं मशीनच असणार आहे, बट on the node on which that process is created. Okay, secondly, or the second field is local identifier generated by the node on which the process is created. It is its local identifier. So the local ID will be having that machine's local identifier, and the third field identifies the last known location of the process. लास्ट नोन लोकेशन म्हणजेच आत्ताच्या एक्झाम्पलमध्ये माझं लास्ट नोन लोकेशन कुठलं होतं की CSC डिपार्टमेंट मधली DBL लॅब. ओके, and then if I am changing it from CSC department to ENTC department and it's a project lab, so that information will also be stored somewhere, but here in this case the third field is having its last known location ID. Okay, so that if any message, if it is coming from that particular location, new location, then I should be able to recognize from which particular machine I am getting this data and what was its previous location. Okay, if the machine is physically shifted from one location to another. So during the lifetime of a process, the values of first two field of its identifier never change. Okay, from which particular node the process is created and its local identifier, that will be the same if you change the location also in that case. Okay, but the third field however may change its value, may. Okay, so this method of process addressing is known as link based process addressing. A process willing to send a message to another process specifies the receiving process I address in the form of machine ID at the rate local ID at the rate machine ID. Okay, so all the three fields will be covered in this kind of process addressing. So although this method of process addressing supports the process migration facility, it suffers from two main drawbacks. Still, this particular method is having drawbacks. The first one is the overhead of locating a process may be large if the process has migrated several times during its lifetime. Previous case what we have seen, if my process will be relocated, at that time what I will do. So for that purpose we have uh, given the solution that your addressing field should include machine ID, then local ID, then again machine ID. But still, if that process is migrated from one location to another several times, then how will you store all this information? Because in our last field what we are storing is this identifies the last known location, right? So it will be difficult to store the last known location uniquely if you are changing its place again and again. So it may not be, and this is the first drawback, and second is it may not be possible to locate a process if an intermediate node on which the process once resided during its lifetime is down. Okay, so जर ज्या पर्टिक्युलर नोड वरती तुमची ही प्रोसेस इन्फॉर्मेशन तुम्ही स्टोअर केलेली आहे, इफ दॅट नोड इज गेटिंग डाऊन, what will happen? So it will not be able to relocate or get its prior information at that particular time. Okay, so in that case some fake kind of information will be circulated in the network. Okay, this kind of drawback will be in picture. So after this we have gone through these two drawbacks over here. With these two drawbacks we are having uh, the problem of location transparency. So what is location transparency? So transparency in the first chapter only we have seen that where is the exact location of your process that should be transparent to the user, right? Transparent म्हणजे transparent नाही, so that user should be unaware that where this particular system is exactly situated, right? So here the problem of location transparency will be there. So, location transparent process addressing mechanism is more desirable for a message passing system is here. A simple method to achieve this goal is to ensure that the system-wide unique identifier of a process does not contain an embedded machine identifier. So for this purpose, a centralized process identifier allocator which will maintain the counter that can be used for this purpose. So here centralized process identifier we will be using. Uh, so when it receives a request for an identifier, it simply returns the current value of the counter and then increment it by 1. Okay. So this centralized process, what does it do? So whenever he will be getting the request from any of the resource, he will maintain its a counter that from which particular uh, uh, process he will be getting the request. Okay, and whenever next time if he is getting the same or any other request, he will increase the counter by 1. So in this way, you can maintain the counter. Also, one more method is there, that is that means to achieve the location transparency is process addressing is is to use two level naming scheme from the for the processes. What is two level? So in this method each process has two identifiers, that is a high level name that is machine independent and low level name. These two fields will be there. A name server will be used for that purpose. This name server is used to maintain a mapping table that maps high level names of the processes to their low level names. When this method of process addressing is used, a process that wants to send a message to another process specifies the high level name of the receiving process in the communication primitive. So the kernel of the sending machine first contact the name server to get the low level name of the receiving process from its high level name. Using the low level name, the kernel sends the message to the proper machine where the receiving kernel delivers the message to the receiving process. So just figure out the structure of tree. So from one node you are giving the request. It is going to the parent node, again parent node, and then from that parent node it will be diverted to the specific node. In this way, the structure will be happening in case of name server. So the sending kernel also catches the high level name to the low level name mapping information of the receiving process in a local cache for the future use, so that the name server need to be contacted when a message has to be sent again to the receiving process. Here in this case, the name server approach allows a process to be migrated from one node to another without the need to change the code in the program of any of the process that wants to communicate with it. This is because when a process migrates, its low level identifier changes, and this change is incorporated in the name server's mapping table. However, the high level name of the process remains unchanged. So here, whenever you are changing any kind of means if the changes are happening at the low level, they should be reflected at high level also. So the name server approach is suitable for functional addressing. In this case, a high level name identifies a service instead of a process over here, and name server maps a service identifier to one or more processes that provide that service. So for this approach, if we use this particular approach, we can suffer from the problems of poor reliability, because mapping of the table changing whenever it is necessary, that will be a bit poor reliable and poor scalable also. So because the name server is centralized one here. Okay, so one way to overcome this is to replicate your name server. But if you are going to replicate your name server, replicate means making duplicate copies or copy of the name server. So the same information will be available with another systems as well, but it will lead to extra overhead needed in keeping the replicas consistent. So if I am changing the data on one machine, on one server, it should be reflected at the same moment of time to another systems as well. So to maintain this data, or to maintain uh, consistent data on all the replicate name servers is a bit overhead. So this is nothing but the process addressing. Any doubt till now? मॅक्सिमम याच्यावरती तुम्हाला व्हॉट इज प्रोसेस. Okay, so if you are asked any question, that is what is process addressing or so, so at that time you should answer it with this explicit addressing, implicit addressing, then its feature drawback, then the first method according to the marks, then what are its drawbacks, that is your machine id at the rate local id, which we have seen prior. Then after its drawback, you can go to this method, that is machine id at local id at machine id. All the three fields will be there, and then you can uh, add the drawbacks of that methods also, and how the name server come into picture in this. Okay, so if you are having 6 or 8 marks question, you have to explain all the things which are there in the slides. Okay, so next bit is failure handling. So what we mean by failure? So while a distributed system may offer potential for parallelism, it is also prone to partial failures such as node crash or communication link failure, etc. Okay, so during IPC, you may face this kind of problem. So these problems, what type of problems are there that are listed over here? The first problem is loss of request message. So here in the diagram itself, it is shown sender is sending its request, but somehow your data is getting lost and it is not properly reached to the receiver. Okay, so this may happens either due to the failure of communication link between the sender and the receiver, or because the receiver's node is down at the time of request message reaches there. So if in case communication line failure is there, or your receiver is not accepting the data at that time, also the message from the sender may get lost. So this request message may get lost. So this is the first condition. Then second is loss of response messages. So this may happen either due to failure of communication link between the sender and receiver, or because the sender's node is down at the time of response message reaches there. It is shown also in the pictorial form. So sender is sending the request message. It is successfully reached to the receiver. Receiver is executing that particular request and sending the response, but the response is lost in between. Okay. So what are the different reasons for this? That again the communication link is getting failed. Okay. Or while sending the response message, your that sender is down. Sender's node is down. Third condition is unsuccessful execution of the request. So this happens due to receiver's node crashing while the request is being processed. So sender is sending the request. Okay, it is reached to the receiver also, but while executing that particular request, this receiver is getting crashed. So then at that time he will not be able to give the response. So this is unsuccessful execution of the request. This is the third condition. And the okay, only three conditions are there for the failure. So to cope up with these problems, a reliable IPC protocol of a message passing system is normally designed based on the idea of internal retransmission of the messages. So internally we have to manage retransmission of the messages after say for example some kind of a timeouts, and the return of the acknowledgement message to the sending machine's kernel by receiving machine's kernel. So that is the kernel of the sending machine is responsible for retransmitting the message after waiting for timeout period, and if no acknowledgement is received from the receiver machine within this time. So the kernel of the sending machine freeze the sending process only when the acknowledgement is received. The time duration for which the sender waits before the uh, retransmission the request is normally slightly more than the approximate round trip time between the sender and the receiver node, plus the average time required for execution of the request. So here for um, setting this the timeout period, you have to check how much time after sending the request and getting back the reply. So how much time is required over there? So that time plus slightly more time you have to set. That is nothing but your round trip time. So that is set for the timeout period. So based on this idea, that is timeout idea, a four message reliable IPC protocol for client server communication is developed between two processes, which is working as like this, which is shown in the diagram. So how it executes here, the diagram is shown. which we have seen last time, that is dotted line is showing the blocked state, continuous line is showing the executing state, and this is nothing but the four message reliable IPC protocol. So how this is taking place? So at the first stage, the client sends a request to the server. Client is there, server is also here, and client is sending the request to the server. Then secondly, when the request message is received at the server machine, the kernel of that machine returns an acknowledgement message to the kernel of the client machine. So here you are finding the acknowledgement sent by the server, that he is getting the request coming from the client. Then after this, third is when the server finishes the processing. So after getting this request, he will be sending the acknowledgement that I am getting your message, and then after he will start processing on that request, and then will be sending the reply. Okay. So when the server finishes the processing of the client's request, it returns a reply message containing the result of the processing to the client. And then after, fourth stage is when the reply message is received at the client's machine, the kernel of that machine returns the acknowledgement message to the kernel of the server machine, that he is getting the reply coming from the server. Okay. So in this period and this period, the client and the server is in the blocked state. So this is the four-way communication or four message reliable IPC protocol. So in client server communication, the result of the processed request is sufficient acknowledgement that the request message was received by the server. So based on this idea, the three message reliable protocol for client server communication between two processes is being designed. So if we check for these particular four messages, which particular message is really not important, and that is this one. So no need to give the acknowledgement of the request coming to the server and giving the acknowledgement from the server. Okay. So to minimize the time for this particular transaction or for this particular communication, the three message reliable IPC is been generated. So this is also shown in the diagram. So in this case, client will be sending the request. Client sends the request message to the server. When the server finishes processing the client's request, it returns a reply message containing the result of the processing to the client. Okay. And then when the reply message is received at the client's machine, the kernel of that machine returns an acknowledgement message to the kernel of the server machine. If the acknowledgement message is not received within the timeout period, the kernel of the server machine retransmits the reply message. Means if for a specified amount of time, if the server is not getting the acknowledgement, he will send the reply once again. So this is three message reliable IPC. So after this, are you finding any kind of drawbacks in this? Drawbacks, or we can say that problems. Um, Problems may occur here if the request processing takes a long time. If the request message is lost in between, it will be retransmitted only after the timeout period, which has been set to a large value to avoid unnecessary retransmission of the request message. So, on the other hand, if the timeout value is not set properly, taking into consideration the long time needed for the request processing, unnecessary retransmission of the request message will take place. So, for that purpose, we need the protocols like first is the client sends the request message to the server. Then, second, when the request message is received at the server's machine, the kernel of that machine starts a timer. So here you have to use a timer for that purpose. Okay. If the server finishes processing the client's request and returns the reply message to the client before the timer expires, the reply server as an acknowledgement of the request message. Otherwise, a separate acknowledgement is sent by the kernel of the server machine to acknowledge the request message. If the acknowledgement is not received within the timeout period, the kernel of the client machine retransmit the request to the server once again. So, and the third protocol is when the reply message is received at the client's machine. Here, the kernel of that machine returns the acknowledgement message to the kernel of the server machine. If the acknowledgement message is not received within the timeout period, the kernel of the server machine again retransmit the reply message. So here in this acknowledgement message from the client to server in the protocol is convenient but not necessary. Here, this particular acknowledgement is not always necessary. So, this is because if the reply message is lost, the request message will be retransmitted after timeout period, right? So, the server can process the request once again and return the reply to the client. So, therefore, a message passing system may be designed to use the two message IPC protocol for client server communication between the two processes. So this is illustrated in the third diagram over here. So in this again, for the first stage, the client sends a request message to the server and remains blocked until the reply is received. So this will be showing you the blocked state. And then after second stage is when the server finishes the processing the client's request finishes processing the client's request, it returns a reply message containing the result of the processing to the client. If the reply is not received within the timeout period, the kernel of the client machine retransmits the request message. Okay. So based on the the protocol of this figure, an example of failure handling during the communication between two processes is shown in the figure on the next slide, that is this one. The protocol of this figure is said to obey at least once semantics, which ensures that at least one execution of the receiver's operation has been performed, but possibly more. It is more appropriate to call the semantics the last one semantics because the result of the last execution of the request are used by the sender. Although earlier abandoned executions of the request may have had side effects that survived the failure. Okay, so this is the last diagram for the failure handling process. So it will be including all the scenarios that are discussed in this process. So here the client will be sending the request. Okay. So after sending the request, it will be setting some timeout period. So if which three scenarios we have seen, that sending message failure, receiving message failure, or the um, हे काय ते execution crashes. All these scenarios are included in this particular diagram. So how the fault tolerance communication between the client server is executed, it is shown in the figure over here. Okay, so here client will be sending the request, but and at the same time it will be setting the timeout period. If that message, request message, is lost, okay, so after this timeout period he will be retransmitting the request message. Okay, so this retransmission also is done. At that time again the timeout period will be set. The second scenario which we have seen for failure is this message, request message, is successfully received at the server side, but at the time of execution your server is getting crashed. Okay, so after this timeout again the sending request process will start. Here the server machine is crashed, but it will again be restarted. Okay, so this, after this timeout period, again the sending message or sending request is generated from the client side. Then again the retransmission of the request message is done. After this this successful request execution, here some kind of execution is being done at the server side, and he is sending the response message, but while giving the response also your message is getting crashed because of some reasons. So again after this time of period, again the request message will be generated. So then here it will be successfully received, again its operation will be done. That means, what type of, whatever the type of processing is there, that will be done, and again it will be sent as a response message, and here your client will be successfully getting the response from the server side. So whatever which we have discussed for failure handling, that is loss of request, loss of response message, unsuccessful execution of the request, then um, the four-way, three-way, and two message protocols, all are described by using this particular diagram. So this is called as the example of fault tolerant communication between client and server. Okay, so this diagram is very important, and this may be asked for 6 marks for the question, for the exam, that explain failure handling. Okay, so at that time you should be able to answer this one. Okay, so now we will stop with this point. You can put your, and before that, if you have any doubt you can post it on the chat. If no, you can drop your attendance in the chat window and can leave the chat.